Okay, we're going to talk just a little bit about some basic chemistry concepts. Nothing terribly deep, mind you, but some concepts that you'll need to understand to get through the rest of the class. So, general concepts, matter and energy. And matter and energy are essentially the same thing. If you've heard of Einstein's E equals mc squared, that really just shows that the energy equals the mass times the speed of light squared. So they're essentially the same thing. We're going to talk about chemical bonds. This is how atoms bind up together to form different compounds, and chemical reactions, the specific reactions that chemicals go through. And we won't focus too much on the chemical reactions. So, matter, just a definition of matter, is anything that takes up space. It has mass, it has weight, and it can exist in different states. So, solid, like ice, liquid, like water, and gas, like steam, are all different states of the same substance. Now, energy is the ability to do work. And there are different categories of energy. We've got kinetic, which is energy of movement. So a car going down the highway has a certain amount of energy in it. And then there's potential energy, which is stored energy. And potential energy can be in lots of different forms. You can have chemical energy, such as stored in the bonds of substances like gasoline. You can have potential energy stored in batteries. You can have potential energy stored by sitting on the top of something, and when it falls, it's got energy. So, chemical energy is stored in bonds. Electrical energy is the movement of charged particles. Oop, little typo there. I'll have to correct that. But it's particles. Mechanical energy is directly involved in moving matter. And then there is radiant energy, which is electromagnetic waves, heat, light, radio, things like that. Now, energy can energy can change form from one to another. So the chemical energy in gasoline will become mechanical energy to drive the pistons, and radiant energy in form of heat. It also becomes electrical energy in that it is driving the alternator, which can run radios and other things. Chemical energy in food is what we use to convert to usable mechanical energy for our bodies, and it's stored in our bodies in other potential energy forms. Now, in terms of matter, well, elements are fundamental units of matter. Elements, all the atoms of a certain element have similar characteristics. They all have the same number of protons, for instance. So that is, in fact, what defines what an element is how many protons it has. Atoms are the building blocks of elements. And we have a variety of atoms that make up our bodies, but there are four of them that make up the majority of our bodies. And that's carbon. Carbon is in all of the organic materials that we have, whether it's fats or proteins or carbohydrates. Those are all carbon based things. We have oxygen, and our bodies are largely water, oddly enough. And so, oxygen and hydrogen, which are the two elements that make up water, make up the majority of our body. And then we have nitrogen. And nitrogen we see in amino acids and proteins. Now, just general atomic structure, there is an inner part for every atom which contains protons, which are positively charged particles, and neutrons, which are neutral. They have no charge at all. Now, these two items weigh about the same or have the same mass. Outside, circling, we have electrons, which are circling the nucleus, and they have a negative charge. So you can say that the negative charge of the electron is drawn to the positive charge of the proton and encircles the atom in that way. Electrons have almost no mass at all. Now, some examples: helium atom has 2 protons. It also has 2 neutrons, and it has 2 electrons. One thing that we see with atoms that are unreacted, now we have to clarify that they're unreacted, but atoms have generally the same number of electrons that they do protons. Now, there are different models. We're going to stick with the planetary model, not because it's most accurate, but because it is easiest to explain, and for our purposes, it works just fine. So in this model, we'd have a proton and an electron. And because we have 1 proton, that makes hydrogen. Now, the more protons you have, the different elements you have. So helium has 2 protons, and lithium has 3 protons. And you'll notice that we have the same number of electrons as we do protons in each of these elements. Now, to identify what element we're talking about, we've got atomic number. An atomic number is just counting how many protons we have. So we have 1 to 92 elements that are naturally occurring, and what we're looking at is between 1 and 92 protons for those atoms. Now, atomic mass, I told you that neutrons and protons have about the same mass. So the atomic mass is the sum of the protons and neutrons that are within atoms. And atomic weight, oops, I apologize. Yeah, no, I did get that right. I apologize. Atomic weight is the average mass of all the isotopes. And an isotope is a variation of an atom that has a different number of neutrons. So you've heard of carbon-12 and carbon-14. Carbon-14 is the one we use to date how old different things are, because eventually it will break down to carbon-12. Now, so let's get to isotopes. They have the same number of protons, but vary in number of neutrons. So hydrogen, by itself, will have 1 proton, 1 electron. Deuterium, which is just another form of hydrogen, also has 1 proton, but it has an additional neutron. And something called tritium, still hydrogen, but it has 1 proton and 2 neutrons. These are all the same element. They just are isotopes of that element. And over time, they will all break down to having 1 proton. Now, atomic weight, and that's different than atomic mass. So close to the mass number of the most abundant isotope. So for the most part, we look at atomic weight of hydrogen, and it's very close to 1. Yeah. Anyway, atomic weight reflects natural isotope variation. That is, it's not going to be exactly 1 for hydrogen. It's not going to be exactly 4 for helium, and so forth. Now, radioactivity, a lot of radioactivity comes from the fact that isotopes want to break down. So we have a heavy isotope which has a larger number of neutrons, and those neutrons want to escape. And they tend to, so those atoms tend to be a little unstable, and they decompose to a more stable form. So again, hydrogen with 2 neutrons is going to break down to hydrogen with 1 neutron, and then hydrogen with no neutrons over time. And that's going to release a little bit of radiation as it breaks down. So we can use isotopes to do work for us as well. In the medical field, we use radioactive isotopes of iodine on people who have thyroid problems. And iodine naturally accumulates in the thyroid, so if we want to destroy the thyroid without destroying anything else, then we can give them radioactive iodine, and it will lodge there and break down the thyroid gland. So, now, atoms react, and when they react, they cause new compounds. So, a compound is where we have two or more different atoms. Molecules are two or more of the same atom. Although we'll use these interchangeably, we'll talk about a molecule of water as opposed to a compound of water. But you can combine two chemicals, two elements, and get something that has completely different characteristics than either one of the original ones did. You know, sodium is a silvery metal that's very soft. You can cut it with a butter knife, and it's highly reactive. Chlorine is a poisonous gas, also highly reactive. But you combine the two, and you've got table salt. So, table salt is completely different than the two constituent atoms or elements that make it up. Yeah, chemical reactions. Atoms are held together by chemical bonds. And when those bonds break, or you can break those bonds, you can get some energy out of the process. You can also put them together and get new compounds when differing atoms unite together. So, electrons and bonding. Electrons live in a space around the atom in something called an electron shell. And there are only so many electrons that can fit in each shell. So the inner shell, the very first shell, only holds two, for instance. So hydrogen and helium occupy the first two shells, or first shell. The two electrons of the first two shells in those situations. Each shell has a different number or an upper limit. So shells to the nucleus are going to fill up first, and then the next shell will allow 8. So bonding involves sharing of electrons to get the ideal amount, and the ideal amount for that second layer is 8. The ideal amount for the first layer is 2. So if I have something that has 6 protons, I'm going to have 6 electrons. So I'm going to have 2 electrons in the inner shell. I'm going to have 4 in the outer shell. Well, that is short of the ideal 8. And so that atom is going to react with other atoms so that they can share electrons and get essentially the same, get a amount of 8. They can tell everybody in a way that they are full. You know, I have a 2-car garage. I have 1 car. My wife has 1 car. Now, it's my wife's car, but we share. And my car, she shares with me. The fact is, we both have our garage full. But if someone were to ask me how many cars I had, I'd say I had 2. If somebody asked my wife how many cars we had, she'd say 2. There aren't 4 cars. There's 2 that we share. And because we're sharing, our garage is full. We're going to stop here and pick up the rest on a second presentation.